Okay, hi, this is Amlan. I am a professor at University of Calcutta and also at IIT Kharagpur, presently visiting. Okay, I don't know how many of you know these two institutes. Anyone here? Yeah, you know, right? You know. Okay. So University of Calcutta is the oldest university of India, 1857. It started, and IIT Kharagpur is the first IIT of India. Okay, I think 1960, I think it was founded. So I am very lucky to be part. That means I am 20 years. I am with University of Calcutta, but from this January I have shifted. Okay, a sort of a visiting position, but most probably that means I will shift in September permanently to IIT Kharagpur because they have started a department of AI, and they have actually that means asked me to stay back. Okay, yeah, so that's okay. So now what I will speak today, right, due to my so my US background. Okay, my first US visit was in 2007. I was doing PhD at the institute called Indian Statistical Institute. I don't know how many of you know that. Indian Statistical Institute in my city, Kolkata. Okay, I started my research on quantum logic synthesis. Okay, and that point of time, I got a visiting researcher position in sunny Buffalo. So my first visit in US was October. Okay, Buffalo, right? And you can imagine, okay, and my place, Kolkata, is a hot and humid, climate, right? From that October, okay, the East Coast, higher East Coast, you can imagine what was my first scenario, but it was a very good experience for me in sunny Buffalo. I worked with a professor called Professor Ken Reagan in Department of Computer Science. Okay, he was a phenomenal professor, and we started a research work in the Starbucks, okay, 2007, okay, where we were trying to formulate the polynomial formulation of quantum circuits, right? And the professor was actually, he was on his own mood and just going on the tissue paper, right, Scrabble the notes and all these things, right? And then I finished my PhD. I got the position in University of Calcutta. 2016, I invited the Professor Ken to my university for a month stay, and then we finished the paper and published it in 2017. So that is one. And then obviously I came to Princeton in 2011, and I worked as a postdoc in the Department of Electrical Engineering, and that was a fantastic experience. Princeton, I think all of you know the experience you get in Princeton is a lifetime experience. So I was very lucky to work with Neeraj Jha and Professor Margaret Martinosi. Neeraj was from electrical engineering, and Martinosi, again, both are phenomenal professors, and Martinosi, and we developed the first. That means I was very privileged to be the part of the team of 15 researchers. Maybe I was the one of the most junior-most in that team, and not only from Princeton, from different universities of USA, because that time the quantum computing project was working with almost 10 top universities in US. So we developed the fast quantum programming language called Scaffold. If you look into the paper for Scaffold, you will find my name, Amlan Chakrabarti. Okay, so I was very lucky, and then we developed a first quantum tool, right, before this IBM Qiskit, called fault-tolerant quantum logic synthesis, which is still in the Princeton archive, right? And we developed it. So then I came back from Princeton, right? And due to some reason, I couldn't. That means I visited so many countries, right? Germany, I visited multiple times. UK, I was a visiting professor at Cambridge in 2018. But I couldn't visit US until 2023. One was that I had a plan in 2020 to come to US for a long trip in Princeton, Buffalo, all that, because at that point of time I was an IEEE Computer Society distinguished speaker. So all my travel was supposed to be beer by IEEE, but COVID started. Okay, I couldn't plan my 2020 visit, and 2023 I was in US, and from there I am now coming to US every year. Mostly in June, because there is a big conference, DAC, Design Automation Conference, what I attend. This year it is a little bit late in July, so I'm just rushing because our semester already started. Okay, so now come back to my work. Obviously, I work obviously quantum computing and AI, right? A lot of due to the research projects, I work a lot on the cyber physical systems because research projects and company projects are very good in cyber physical systems, right? You can build some firmware and you can just that means just offer them for the solutions. Okay, so my lecture will be mostly on those things. I will not discuss any research here. Okay, I will just try to give you the accelerated technology, okay, which is now moving very fast, okay, in the domain of the computing, data, and infrastructure. So my talk will be based on all these three things. Okay, yeah. So let me. So this is the agenda. I will try to keep my 45 minutes. Okay, my lecture. Okay. So yeah. So this is the agenda where I will try to what is compute. Okay, data. Okay, data is now the what I can say the main gold mine, okay, for computing, right? If you try to look at them, if you have data, right, that means your computing is powerful. If you don't have data, right, your computing is not powerful enough, right? And we discuss what is this AI triad, okay, right? The data, HPC, and accelerators. Though I will focus on the quantum accelerator here, okay, but there are a lot of other accelerators also coming up, right? And we will try to look into what AI is going to do, right? AI has evolved, right? AI is not only prediction and classification, right? AI is actually that means visualization, right? AI is now coming as understanding. We understand through AI, right? AI helps in our understanding, right? So it has been transformed from the tool we developed, okay, to a tool which supports me. Okay, so it has, okay, but that way it has evolved AI in that way, right? And that is the thing we discuss. And in order to do this, right, we require a lot of computing evolution has come up, right? And the technology that means that means we come up to a new technology when we face bottlenecks, okay, in our older technology, and that AI has pushed, okay, some technologies to which were actually reaching the almost saturation, okay, to get out and take a new path, okay, right, and try a different direction, and that technology got emerged. Okay, that means if you see the computing from the multi-core, saturated, and then GPU took off. Okay, so those are the things which came up. Okay, right, and obviously that means how we support the real scenarios. Real scenarios will obviously take all these things and try to make the very advanced cyber physical systems. Okay, which will help the society. Okay, be it health, be it environment, or be it agriculture. Okay, there are a lot of use cases we have done because I have done many projects in my country, both from the government and from the corporate, but I will not get into, I will just give you a few glimpses on that, okay? Right, and then obviously I will put that what is the next scenario, the quantum, okay, right? And obviously when we have all these things, we also have to see that when we develop a technology, the technology can itself bring some challenges. The quantum we are bringing up, but quantum, one having a strong quantum computing, tool or system, right? Okay, that can be very, very, if wrongly used, can be very dangerous. Okay, so it's how to look into those aspects of quantum too. Okay, and then I will conclude. Okay, yeah. So what we see is basically, that means I'm just from VLSI conference, so I thought that means obviously, okay, that be it design is the way I try to gather the requirement, right? And from that we try to find out that what are the components of my system. That can be the preliminary design, and then we try to make more finer components in my system, and I go on doing that, and that becomes my design. Okay? Okay, now in design, we do something called exploration. Okay, exploration means that there are some functionalities, okay, there are some resource axes, function axis, and cost axis. Okay, right? You need to come to a region in this space so that you satisfy the constraints in the terms of your functionality. Functionality has some constraints, right? You can do this, you cannot do that. Okay. Okay. Resource has budget. Okay. Time is also a constraint. Okay. So it is basically solving this big problem is design, right? I can say that that means I can just take some components and say that these components will work, but these components will not work because your design, it is not a design. It becomes a design if you can satisfy all these rules, what is being laid from that particular problem specification. So there are a lot of explorations are required, where predictions are required, and multiple options are there, which options to take. Okay, right, and these are connected things. That means you cannot converge the design in one step. You require multiple steps, okay, to converge the design. So how to estimate what will happen when I go 5 steps forward? Okay, those earlier people would have gone 5 steps forward and then found that, oh, I got stuck. Okay, right, now AI is there where you can actually visualize what will happen after 5 steps. Okay, right, and you can estimate that, oh, after 5 steps this will happen, and this is within my budget, so I can go ahead. Okay, fine, or not. Okay, so those are the things which are being done, and obviously the other part of this thing is that you require different expertise, okay, for design, because though I'm telling you just aggregate the components and try to reach your functional requirement, but the components in a very complex designs are not coming from one domain. Okay, components are from various domains. Okay, so some expertise you have, some expertise you don't have. Okay, so that's why also AI is helping, because AI can always substitute expertise with its own intelligence. Okay, provided there are existing models in that particular domain. Okay. So I was discussing with one company, right, analog design. So I have an industry background, which is EDA. I was in Cadence before I migrated to academia. So I have an EDA background. That's why I still get called in these design automation conferences. So so we know that analog design is pretty complicated. Those who have a little bit idea of analog design is pretty complicated because it is continuous, because you have to observe the signals in a continuous way, and that means the certain variations are also very different. Like digital have very stepwise variations. Analog has all the different forms of variations. Okay, so simulate an analog design takes a lot amount of time. Okay, so I found a company which is trying to generate a neural model for analog design just for simulation. Okay, so analog circuit will be represented by will be replaced by the neural model. Okay, right, and now you have a lot of test inputs and try to see that whether this circuit will actually work in simulation. So those are the things we can do in design, right? And next we go to simulation also. I said, right, okay, design is exploration, right, and simulation is verification of the design. Okay. Second is virtual prototype. This helps so much. Virtual prototypes means you don't have that particular, it's very costly. Some of the domains are very complex. So before getting into the actual physical prototypes, you want to see that means if I build this, right, of this particular functionality, of this particular design, right, what will be the outcome? Okay, it's a sort of a visualization of the physical entity in the virtual platform. Okay, right, and digital twins and all these things we know. These are now, okay, now we see for in construction engineering, okay, right, in medical equipments, okay, right, in many of the critical scenarios, we don't actually build it and test it, but before we try to make a digital twin, right, and try to see everything what is going on. And these are basically the game of the data, okay, right, and intelligence together so that you can represent a very complex, complex process, right? And you can also make all sorts of operations on the complex process in the virtual domain, okay? Right, and this all this helps to applications such as intelligent manufacturing, okay? It's so important that you have the, that means all your AI engines are now actually controlling the manufacturing process, okay, starting from the design, fabrication, okay, packaging, all the things are now being controlled in this particular way by the robots and automated processes, okay? Right, and automation that means autonomous operations, we know, right? Unmanned ground vehicle, unmanned aerial vehicle, right? That means we have driverless cars, and right, all these things are also, these are the outcomes of what we actually look into the confluence of actually data, AI, and systems. Okay, so data, AI, and systems confluence are actually making this new type of systems, okay, new intelligent systems, right, which are still evolving. We don't know where is the limit, okay, right? And if we look into this, this scenario, we see that, okay, these are the things which are happening. So, so physics or science, right, so that is now, now being well absorbed in AI, because many of the times we don't have the, what I can say, you cannot actually, that means you just have to take a prototype of the science, science function or the science operation. Okay, so that can be very well represented by an equivalent AI model. As I said, the analog circuits. Analog circuit represented by its equivalent neural model. Okay, or I was actually listening to a lecture of Preet Banerjee, who is the CTO of ANSYS. Okay, they are telling that when we try to manufacture the body of an automobile, it's a very complex work, okay, because you have to take care of so many parameters. Okay, it's a very, very complex physics, right? And when we try to solve it only in the physics way or material science way, there will be some error because all our science actually leads to certainty. Any science actually goes with a certainty logic. Okay, you have a particular physical law, you have a particular mathematical function which defines your science. Okay, but in the real world that will not happen. So there is some uncertainty. Okay, so he was telling that science will give you the certainty, and your machine learning will give the uncertainty. So wherever you see the certainty cannot work, you take ML into consideration. Suppose the health of the tire, the health of the tire of a car, right? Though you can tell that there is a the tire has this amount of tension, elasticity, and this is the condition of road friction. You can make a mathematical model, but it's very difficult. Okay, so you have to get that uncertainty with that particular AI, and you have to predict that if I prepare this particular tire for this particular car, what is the average lifetime of that? Okay, so so these are the things how we do it, right? And the second thing which has come, I think, for 1 year is that instead of making a very large AI model, which is costly, which is not also in that sense good, because you cannot have that amount of learning complete. You cannot have a complete learning of a large domain. Okay, that's a very challenge for our AI model. So what you do, you make multiple agents. Okay, so you try to split the entire problem into multiple sub-problem and train your agents for each of the sub-problem and make an agentic type of philosophy of AI instead of making one engine for solving the problem, right? Make multiple engines so that it's also good for us. That means you might be in your solution, you might not be in some of the solutions, you might not be requiring all engines. Okay, so your cost is also very balanced. Okay, right? But if you are taking one single engine, maybe in different instances of an application, you are only using some power of the engine, not the entire power of the engine, but you build the engine so that means so that it can work for everything, so its cost is enormous. So that's a way you save your cost, right? And you also go more accurate, because now your agents are perfectly trained for the smaller domains. Okay, and for the smaller domains, the learning can be very well done. Okay, that's the thing of agentic AI, which has actually got a very good success for the okay, that means in the last 1 year. Okay, and the third, which is pretty important, is that means how the AI will interact in the physical world. Okay, presently AI runs in my server. Okay, right? AI runs in an environment where I feed AI, I get the output from the AI, and then I give it back to the end user. Okay, right? So can AI be an engine which will actually work with the physical environment? Okay, that means as it's on its own. Can it work on its own? Okay, right? For that, you require not only that the AI generates some outcome, but you also have to have reasoning in the AI, because otherwise it will fail in the real scenario if it doesn't have because human is successful. Not only that I have been said by my professor or by my senior member of my family that you have to do the task in this way, though I start in that way, but then I find a reason that there are something which I have to do on my own, because I have that reasoning power, that what I need to do when the things are pretty different what I has been told. Okay, that's called the reasoning power, that you don't do it as a one block operation, but you try to take steps and try to reason each of the work what you are doing. Okay, so that is very much required when we do in the real scenario, because the physical AI will be interacting with the real scenario. Okay, right? It is not only a tool or a system at the back end. Okay, so these are the three things which are very, very strong strong power of AI, and the entire AI research and AI development, if you look, is going into these three particular directions of AI. Okay, right, and in order to get this AI, right, this form of AI. So so I will tell that AI is not only prediction classification, which we used to. Normally we will used to mean that AI means like that. It is much above that. Okay, now right, we require a lot of the computing resources, and right, and for that it is not only the parallelism in AI, but we also require performance. Okay, performance means that if I offer a quanta of resource, how much amount of advantage, right, in terms of your storage and computing I get. So what is the ratio? Okay, what is the ratio of resource versus performance? That was not very good, but now we are trying to make the resources also efficient. Okay, right, in terms of the efficient memory, right, in terms of the on-chip optical networks for your data communication, and obviously the architectures like GPU, TPU, all these architectures are actually making your compute infrastructure also very, very high performance. Okay, high performance memory, high performance data communication, and high performance processing, which is also the backbone, right? And the third is it should be scalable. Okay, right? We can expand. Okay, right? As required. So that is still a little bit of bottleneck. Okay, you cannot just go like that, but probably the quantum and those technologies, right, probably will give you a higher scalability, right, in terms of the data and the processes, because scalability means that what is the ratio of your resources to compute. Okay, so so this has all resulted to very, very impactful business impact. Very high business impact. Okay, shorter design cycles, saves my cost. It's higher accuracy, gives me a leader in the market. Okay, operational excellence, I manage my team well, okay, right? I use every resource in the, okay, right, in the best way. Operational functional means that, okay, that means I use every, okay, so my resource estimation and its utilization are being very, very well solved, okay, and obviously sustainable. Okay, that's still questionable, right? Whether, okay, that will lot of debates occurring now, right? Whether AI is sustainable or not, okay. But my pitch is that the technology is always there, okay, so that we need to think on sustainable AI. Okay, okay, so that is obviously, okay, that is a good thing to do research, right? How we can make the AI sustainable, because if we just don't think on that, we will not able to sustain AI. Okay, okay, but there are some challenges which are there, right? Okay, there are challenges. The challenges are the, okay, one important thing is that, okay, that means if you are trying to absorb something in our AI process, the context is very important. Okay, context means okay, a sort of a correlation between what I have got now, what I had in the past, and what will be coming in the future. Can we establish the correlation, whether I'm taking the things without context or with context, because the power of context is very much required, and in the human, and if we tell that the fundamental thing, the AI is just imitating human, okay, it means that we have to be very contextual, and we in human can actually work on very long contexts. Okay, unlike I say, right, I started a work with Professor Ken Regan in 2007, right, and finished the paper in 2017. Okay, one of the example of very long context, right? Both of us remember that what was our key discussions, okay, and tried to work on that. Yeah, that is an example, but I'm trying to say that this is very much important, and many of the times we have seen that AI fails, right? What it is telling now, it is contradicting what it has said just a few iterations before, right? It's contradicting, right? And I can do it knowingly or unknowingly. I can make my AI contradicting. Okay. Okay. Yeah, as a hallucination, one of the good examples. Okay, when it goes out of context. Okay. So these are the things obviously are very much required, and obviously it has to work with the real data pipelines also is very important, right? It's not that though I train with the history data, okay, but ultimately performance of AI will be good what it is doing in the real data. Okay, okay, so it means that our training is good, okay, but performance depends on how it works on the inferencing. Okay, so we have to always grade my AI and make the performance of the AI on the inference. Okay, okay, right? And obviously what happens is that the understanding, the visualization, the communication of AI was previously, okay, AI system, okay, generates something and that is absorbed by a human, okay, passed to another human, and then it again goes to the AI. Okay, this was a sort of a flow, but now the two AI systems will communicate with each other. Okay, right? And how this communication will work. Okay, how this exchange will work, how the data exchange will work. Okay, suppose an API from X application and okay, talks with an Y application, and both are AI application. Okay, right? How we will make this work together, right? Okay, these are some of the challenges. Okay, and obviously we have to take an integrated approach rather than that means each of the functionalities are being taken by different AI engines. Okay, so either we do agentic AI, where there will be a coordinating agent, coordinating master agent, and okay, right, and there will be all these agents which are child agents, right? Or we try to take it as a single problem and try to fix it out, which can be a problem, but we cannot run in our organization. We cannot run a purchase AI, okay, sales AI, right? Production AI. We cannot do like that. Okay, we have to, because previously it was like that. I know many companies actually only focused on, okay, I require a tool for sales analysis, right? And that is completely disjoint from the purchase. Okay, so it failed, right? Okay, right? And the second thing is that it has to be very precise. Okay, precise. There are two things what I have focused here is that one is that means you have the legacy infrastructure, okay, which needs to be properly taken care of in the AI building process. Okay, because lot of information exists there, okay, right, and you cannot throw off that. Okay, so that is one of the challenge also. Okay, how to orchestrate that. Okay, legacy into your modern AI, and many of the organizations are actually getting a sort of hindrance. Okay, AI adoption. This is a challenge in AI adoption. Okay, I can start AI from today, okay, from the data which is generating now, okay, but then I cannot use the data, okay, which was working in my organization for the last 10 years. Okay, how I can take that pipeline, okay, in my present AI pipeline seamlessly. Okay, so that is there, right? And obviously it's a continuous intelligence, means intelligence cannot be static. Okay, if you tell that, okay, that means I have built a model for my last 10 years data, right, and this model will work for next 5 years, no, it can't happen. Okay, this model can work, but simultaneously, okay, that means you also have to adopt the model, or you have to retrain the model, and you have to go with continuous few shot learning of the model for the new data which is coming up, because otherwise you will be drifted. Okay, your model will be drifting very much. Okay, right, and that is also a challenge in adoption, AI adoption. Okay, that means how I can make my model adaptive, okay, to the, okay, because the things gets changed nowadays in terms of business, in terms of your perspective of clients, the things gets changed very fast. So do we have to make again start from the scratch and build a new model for this change? Okay, or we can adopt the change in my model very smoothly. But these are still the challenges. Okay, right, and obviously on the topmost of that, there are a lot of data gets exchanged, a lot of digital footprints gets generated. Okay, right, and you have to very sure that, okay, this is security is there, right, because everything beings on data, right? If your data gets actually corrupted, right, or the model is also built with data, because model has the weights. Okay, model parameters are the data for the models, right? If the parameters gets changed, your model gets changed. Okay, so this is also something, okay, which is critical. Okay, so now there are challenges, but obviously, looking forward, we have to think about the three very powerful, very powerful components, okay, right, which exist in the domain of AI. We call AI triad. Okay, so data is one of the things where we have to be very focused. Okay, second one is your compute, which is basically high performance compute, massive parallel computing, and storage, and large storage, right? And accelerator, I have put it quantum due to the Okay, due to the quantum I want to pitch to all of you, that's why. Okay, but there are different accelerators which are there for for HPC domain. Okay. Okay, so this is, I will not now go into very details of this, but this is the flow of the data in an AI scenario. Okay. Okay, the flow, that means many of the times we cannot get the full data in our hand when I start building the model. Okay, because it's very, because this is a chicken and egg problem. Okay, data is not there, so I cannot build the model. Okay, right. When data comes, right, the model, the requirement of model is prior to that. Okay, I require the model now, not after 2 years or after a year when the data is sufficient with me. I require model now. Okay, so the thing is that you start with a small amount of data. There are techniques where we can generate the synthetic data, build a first-hand model, first version of the model, the pre-trained type of model. Okay, right? Actually, then collect the data from your sources, right? Right, and again you try to retrain the model. So it can be a sort of transfer learning, what we say technically, right, or knowledge distillation. Okay, you don't have the exact domain data, but we can have a large data, okay, either synthetic or available, which is a little bit different domain, but still you can work with, and then you can slowly you can make your model more very focused, okay, on that. And then obviously, okay, there is something called RL. Okay, so it's called the base model. We start with a base model, right, and then we actually train the base model to base model is called a pre-trained model, okay, which is being generated with some data which might not be my data, okay, my very code data, right? It can be data which is from a very large distribution, okay, right? And then we try to generate the trained model, right? And the trained model on the runtime will again learn through a feedback which is called the reinforcement learning, okay, and will actually try to again retune the policies of the model. Okay, policies of the models in a very naive way are the weights of the model. Okay, the weights of if we are going neural network, right, the weights actually define that what will be the outcome. Okay, the way the weights are being decided. Okay, right, and that actually defines that which path will have an higher existence for a particular scenario. Okay, right, and so when we see that the model is not performing good or the model is failing in some context, right, we can give a feedback and we can actually squeeze down some paths or we can expand some paths. Okay, because those are the policy adjustments which we have to always do. Okay, right, and that will ultimately lead to a intelligent decision action sort of activity which the AI can do. Okay, so this is the most generic way, okay, of telling that how you actually build the model, okay, in AI. Okay, right, and obviously with the compute requirement, okay, this particular diagram shows a sort of a compute requirement like this. So so what we do, that means, okay, when we try to take the model at a full, we require the most compute. Okay, right, at the start we can actually come with a lower compute, right, and once we freeze the model and we are only doing some minor updates of the model, we can require a lower compute. Okay, so computing requirement also varies in the life cycle of your model. Okay, fine, and so it is, okay, so the focus is that continuous learning, as I said, it is not a static model. Okay, right, you have to learn the new things, and you have to might be unlearn also sometimes. Okay, right, and that generates data to intelligence. Okay, better decisions. Okay, because it is not based on some rules. It is based on data-driven decisions. Okay, and reliable and scalable. Right, you can always, it is reliable because you're always taking a feedback. Okay, right, when you Okay, when you see your model is not working well, okay, right, you update the model. Okay, so your model is always up to date. That's why it's reliable, right? Right, and scalable, because this is the way you can actually build. Otherwise, you will be in a very wrong loop, right? Okay, that means okay, where to start, when to finish, you don't know. So it becomes scalability will not be there. Okay, and obviously the human plus AI is always there, in the sense that, as we are discussing before the talk, that what will be the role of humans in this domain of AI. Obviously the humans, who has the ability to control and to inspect AI, their jobs are fine. Okay, right? Who are not at that level, okay, they have to change to some other jobs. Okay, computing jobs phenomenally will be taken over by AI. And now who will be staying in the computing jobs? Okay, who can inspect AI, okay, who can control AI, okay, who can do an audit of the AI, who can do the auditing of the AI. Okay, right? Yeah, that otherwise if we're not doing that, right, computing will be, that means I cannot go on in computing. I can do some other job better. Okay. So I will not get into details, but I am trying to say that why HPC is required. Because HPC, high performance computing, though it is a scenario that where we have lot of debates are there, right? Water crisis. One of the big debates are there, that why some of the countries are shifting their data centers to other countries. Okay. Okay, right? People are taking up data centers from one country to another country, right? And okay, right? Again, that means after going back to India, I have to make some sort of research work on that. Actually, some of the agencies have said me that Professor, you have to take care of this, come up with some sort of data. So this is a different thing. But ultimately we require compute. Without compute, your AI cannot work. Okay, both compute and storage. Okay, but the direction is that, okay, how to, and that is my present domain of research, right? That means how we can make these AI models, okay, low cost, okay, very fit and low cost models, okay, without sacrificing accuracy. Okay, what are the ways we can build those models, right? But still we require compute, okay, right? And that is basically the many of the cases, like in India. I am not so much knowledgeable about what is happening in US. Okay, there are national missions, okay, on supercomputing, okay, where government of India, I will show you a glimpse of that. Government of India is trying to make two national missions. One is on the supercomputing and one is on the quantum computing. Okay, right? And they want to have that means an integrated nationwide sovereign, okay, sort of stuff. Okay, which will be ultimately achievable or not achievable, time will take. Okay, time will speak, but that is required because instead of making fragmented computing resource, I think also I worked with an Infosys. I don't know whether you know this company. Infosys is a consulting company. Okay, they have origin in India. So I was the mentor of the Indo-UK Accelerate program. Okay, there I worked with a startup. Okay, where we actually looked into the utilization of HPC versus workloads versus the different periods of the day, of the year. Okay, right? What are the workloads variations in the HPC? Okay, right? And can we have some better suggestion of workloads? Okay, when to start which work? Okay, instead of pushing all work at the same time. Okay, can you have a scheduling of the workloads? Okay, based on the energy management of the HPC, because energy management gets directly to the water crisis. Okay, right? See, we cannot say that we will not do. Okay, it cannot be done like that. Okay, we stop it. We cannot stop AI. Okay, we have to do, because otherwise we will be backwards. But the trick is that how to efficiently manage AI and try to find out the ways we can reduce everything. Okay, not stopping the thing, but reduce everything. Okay, that's the thing. Okay, so there are some big problems like the climate and earth systems, which has a large amount of data, very complex. You cannot just make mathematical models for those. You have to do this type of approach of AI, right? Like life sciences and space, and that means all these aspects have got a huge benefit from AI. Okay, and that was mainly because we had the compute power also to do that. Okay, so obviously the organization who has the compute power, there is also something coming up. Like in India, we had a term called digital divide. I don't know whether it is there in US or not. Digital divide means that basically, the people are divided with their digital capability. Okay, which means that some people are very, they have all the digital tools and digital means. Okay, one is the device, one is the communication infrastructure. They are in some locations of the country, and their economic background, they are well acquainted, okay, with the communication infrastructure and the digital devices. But there is also the other side. Okay, there are people who might be equally fit, okay, but due to their inaccessibility of the digital device, either due to the cost and as well as due to the communication infrastructure in many of the locations of the country are not in that level, so they are isolated from the digital world. Okay, right? And so whether there is a divide going on. Okay, similarly, I feel that there will be a divide on the AI. Okay, people can spend for AI, people can accommodate AI. Okay, right? Will be moving faster. Okay, that means it seems. Okay, right? And those who will not able to afford those actually it's not people, it's more organizational level. AI is not people level now. AI is more organizational level now. Those organizations can afford AI. Okay, they will be moving much faster. And those organizations cannot afford AI. Okay, they will fall backward. Okay, so the thing is that we have to actually, so that is also a business idea for AI, that can we bring more people towards affordable AI. Okay, so I think the present research in AI will go like that. Okay, right? And obviously, if we look into the infrastructure, there are a lot of things are coming up due to this affordable AI, right? Don't do all compute in the cloud. Cloud is costly. Okay, can we have edge systems? Okay, edge are small computing devices. Okay, which are very local. Okay, right? Cloud is a massive distributed system. Okay, right? Okay, where we all get connected in some way. Okay, right? But we don't require that amount of massive infrastructure for all computes. Okay, many of the computes can be done at the edges. Okay, and for the physical AI, means when your AI is actually working in different aspects, like smart city navigation, smart city water monitoring system, smart city environment monitoring system, smart city parking, smart city waste management, right? Whether we need to, what we do in edge and what we do in cloud, okay, this needs to be very well planned. Okay, so that we can use it in a very well defined and well orchestrated way in terms of both the infrastructure as well as the intelligence part of that. Okay, so there are well defined now network architectures. okay, well-defined infrastructural models where we tell something like the intelligent continuum, okay, which means that you have the physical device, then the edge computing, then the cloud computing, okay? Where to compute, when to compute, what to compute, okay, depends on certain, okay, certain conditions and certain criteria, okay? If you can formulate that for your application of real AI, okay, then I think you can save in many of the cases, okay? And this is a little bit scenario of Edge AI, right? We are mostly doing work on Edge AI now, okay, where we are going for the things called TinyML, okay? We are actually making this, making this versions like lightweight YOLO versions, okay? And we are looking into a lot of real-time issues, right? Okay, low latency, local decision making. Okay, anomaly detection is one of the very important thing in AI, because in anomaly detection you don't have to infer for everything. In anomaly detection, many of the AI problems can be that means, I'm not saying many, that means obviously there are some AI problems can be very well managed for the user but just doing anomaly detection, okay, which means that whether it has a variance above the threshold, okay, or within the threshold, okay, right? If it is above the threshold, it is class 1, it is within the threshold, it is class 0, okay, something like that. Without that, can we do all these things, right? And that can be very well done in Edge, okay, because you can have a pretrained threshold, okay, which is settled by your data, and then you just make a pretrained thresholding model, running at Edge, which is not very costly, okay, right? The runtime data comes, and we just actually, because your training has already defined the threshold, okay, so you don't need to do anything. You just compare whether the data is within the threshold or not. If in the threshold, right, you don't do anything. If outside the threshold, you flag something. Okay, these are the ways we are, the people are trying to do, and resource optimizations and scheduling and process control is the key areas what we try to do at the edge computing. So there is an Edge AI gateway. So gateway is something that which communicates between your edge and cloud, okay, because this gateway in terms of communication is different, because there is a different communication which goes between edge and device, and a different communication goes between edge and cloud, okay? Okay, normally the edge and device communications are short range communications, because edge is very local to the device, okay? Edge to cloud communications are long range communication. Like you can go for Wi-Fi or optical when we go for edge to cloud, but you can go to device to edge maybe by Bluetooth, okay, by LoRa, okay, those type of okay, low energy communications you can do between device and edge, okay? So those are the things you can do, and you have lot of like your like a controls for your UGV, okay, that means they all go for short range communication. That means hardly they go with the cloud communication always, okay? Yeah, so there are a lot of things, and this actually focus is real-time, reliable, and resilient. These are the 3 things we need to maintain, because these are on-field applications, okay? On-field applications requires more resilience, okay, because security is there at a stake, okay, because a lot of side channels and a lot of actually adversarial attack can happen in the field, okay, and reliability, because a lot of environmental issues comes up, reliability. So whenever you are doing fine, and real time. So whenever doing edge computing, okay, these 3 challenges, real time, reliable, and resilient, these 3 challenges are there. So it is okay. So there is no free lunch. It doesn't mean that, okay, that means edge means you don't have to think anything, you just put an edge and you are very cool, right? It's not like that. So the thing is that edge comes with its own challenges. Okay, yeah. So this is there in every technological aspect, that if you want to generate one particular channel of your progress, right, there will be challenges in that channel also. Okay, but you have to take that, because you cannot do all compute in cloud. First of all, latency, then energy, okay, right? And then obviously that means you are going with a more expensive infrastructure. Cloud cost is more expensive. Okay, so the budget goes high. Okay, so you cannot do that. So many of the applications in the especially in the case of cyber physical systems, okay, goes like, which are working locally, goes like that. Okay, so not get into details, because I think I have maybe 5 minutes or 5 to 8 minutes more. Okay, yeah. So how much time I have? 10 minutes. Okay, yeah. 5
you're a little bit over, but yeah.
Okay, 10 minutes maybe. Okay, fine. So this is something we have done, and this was published in this year in Transactions of Sustainable Computing. So we are going into sustainable computing. So what we did, we tried to that. I mean, now presently all this stuff, that means all this VLM, LLM, right? All these things heavily depends on the thing called transformer. Okay, the transformer is the key. Okay, right, which actually encodes, decodes, right, encodes from your input, right, and actually generates the output from the decoder. Okay. So we need to make the transformer very lightweight. Okay, so we use 3 things actually. Okay, one is the binarization of the weights. Okay, right, and secondly we try to make an early exit. So instead of going through all the layers, okay, if we ask that, okay, that means, okay, say I am going to DataCon LA, okay, right, the question is asked that what topic I will speak. Okay, obviously it will related to AI. Okay, because DataCon LA has a mostly it will be AI or AI allied, means data science and AI allied, right? I will not, okay, that means 70%, 80% will be like that. So there is no point in getting into other resources. Okay, if I find that, okay, this lecture will be hosted by DataCon LA. Okay, these are the things, that means I don't go into much deeper layers now. Okay, fine. But if you tell that, okay, there will be a lecture in the design automation conference, okay, you have so many things can be done. Then you have to go, okay, who is the speaker? Okay, what is his organization? Okay, right? So what he has done for the past 3 years. Then you can guess that what is the topic. Okay, because there can be so many fine-grained things on design automation. It can be software, it can be hardware, it can be AI, non-AI, so many things it can be. Okay, that is the way we can, how many, because each layer in your AI actually works with that means a more complex feature space. So increase the complexity of your decision. That means if your decision is more complex, you go to the next layer. If it is further complex, you add more layer. This is the way the layering in your network happens. Okay, so we try to reduce the layering in the network, right, by using some forget gate and all these things is there. So you can look into the paper. It's the latest transaction paper from our group. Okay, similarly we use that and we try to work on a very real problem. Okay, called, that means as you know that the part of the country where we in the eastern part we have a very Darjeeling tea. How many of you know this term? Darjeeling tea, anyone have heard? Darjeeling tea, right? Okay, so Darjeeling is a northern district of our state of West Bengal, right? And that tea is very, very costly. The original Darjeeling tea is very costly and it goes all over the world. Okay, right? And this tea, tea is a very royal plant. Royal in the sense that if T gets infected in a very small amount also, okay, the cost of the price of the T depends on the sum. I am not a T tester, but there is a very, very T testing, there are experts, right? They define the rating of the T, right? And it's observed that if the T gets infected, okay, maybe a very, very good T plant, its cost will go down to maybe almost 1/4 or 1/8, because that affects the test of the T. Okay, so tea plantation farmers are very, very, that means they are very, very careful about the pest infestation, and they suffer a huge loss. Okay, so pest infestation in tea is a very, very, very strong problem, okay, in our domain. So we try to implement that visual transformer and try to put it on the edge. So it's a real problem. So right, and put some, right, and got some good results which are better, okay, than the earlier ones. And we saw that we have actually put the lower resource, okay, right, our accuracy also didn't gone down, okay, right, and we did this, and this was also published in the ACM transaction this year. So these are all recent works I'm trying to discuss with you. Okay, the last part of this is obviously the trustworthy, right? These are the 4 pillars of the trust, right? Explainability, right? Why your AI system has done this? Why the answer was this? What were the reasons that it has generated this answer? Okay, it shouldn't be a black box. That is called the explainability. Fairness means it doesn't have any initial biasness. It means it that means its inferencing is at the same level for all the subgroups of your distribution. Okay, it shouldn't be that, okay, for one of the groups of the distribution, right, it is actually doing very good, okay, and for the other group it is not doing good. Okay, yeah, reliability means it doesn't fades with time. Okay, it is consistent reliability, consistent over the time, right? A robustness with a certain environmental fluctuations, with certain noise, will it still work? Okay, right. If its performance will degrade or it will work. These are the things which comes to the trustable and trustworthy AI. The most important trustworthy AI we require in human health. Okay, because that is directly connected with the individuals. Okay, and we developed a model and which was published in Nature Scientific Reports again in this year. Okay, first of its kind model where we try to look into, that means that every parts of this health system. Okay, we try to develop 4 metrics, okay, which define the trust index. So we define this term called trust index based on algorithmic transparency, okay, interpretability alignment, and compliance, because in health sector you have compliance to protocols. So based on all these 3, we generate the metrics, and ultimately we decided a trust score, right? And we are happy to grade all the different types of algorithms which are working in the medical analysis domain, mostly image analysis domain, based on our metrics, right? And you can get into the paper called Tax AI, Trust Ever Explainable Framework, okay? Right, I will go to the last part, which is called federated learning. So what is coming up here is that, right, as I said, that there is, multiple agents are there, but when we go to the edge computing type of scenario, right, the learning is also broken. It is so the difference between agentic and federated is that there may be a confusion. Okay, so in case of agentic, the models are completely different. Okay, that means each agent are working with their own models. In the federated learning, the learning is different, but ultimately the model is generated with the aggregation of learning of all these local agents. Okay, so all them aggregates and builds one model. But why it is called a federated? Because you cannot have all the data coming from different sources cannot be pushed into the central, either due to security, okay, because they have their own local data. Okay, they will not give it to a central. Okay, because then everyone will be in the sharing will, that means everyone will be homogeneous. So I want to remain as a different from A, B, and C wants to remain different. Okay, they are different in locality. Okay, but still a model needs to be built up. Okay, that's the way of federated learning. And we also tested the federated learning again on this particular, okay, again on application on T, because that is the data we got more, and we work with the T companies, right, in that space. Okay, and we tried to see that in different T forms. So we worked with the different T forms, okay, for their own thing, okay, right, and ultimately we developed a model which will good for all the T forms, because T forms are the different type of little bit different types of their land form, soil conditions, and it worked. Okay. Yeah, this is also one work we did, which is also that this was a little bit earlier work. In 2020, we published a Journal of Supercomputing, where we shown that there are two primary factors of the energy reduction, okay, to sustainability of this. One is the location of the communication power, right, and another is the compute power. So when we are doing edge computing and cloud, there is one is the communication power. Okay, power we spend for communication, right, and the other is for the compute. Okay, so we try to look at how we can deployment of edges, and the sensors are very important. Okay, the deployment should be energy aware deployment first of all, and the second part is that you need to compute, right? You need to compute. You need to make the compute time. Okay. That is compute time very effectively used. Okay, so we need to make the compute time divided into certain slots, right, and try to put the task on those slots in such a way, okay, such that no slots gets open, okay, gets vacant. Okay, so when you compute to full. When you don't compute, you don't compute. Okay, you are not in between that. Okay, I have finished computing, but there is no task, but still I am on. So we try to define a scheduling algorithm, and we try to look into that. Okay. Okay. So the last part, maybe the last 2-3 minutes, I will focus on what is there in the acceleration. Okay. So, okay. So quantum, as I say that the focus of quantum is that means, okay, it generates an exponential state space. Okay, and it can look into so machine learning in that space is basically learning distribution. Okay, right? And the difference between classical and quantum is that in the classical we actually take each sample and learn. Okay, each of your training record is one sample. So I pass your training set, but I learn. That means I pass each of the samples one by one. Okay, to learn, right? And we take a batch, which is the entire sample set. Okay, we take take an estimation of the batch. Okay, right? And then we try to find what is the error, and then adjust the weights, and then a summation of the batch is your epoch. Okay, so we go like this. So we take a big set of data, divide into batch, and we learn each of the batches, adjust the errors, and go on that. Okay, because we cannot look into the entire distribution at one shot. The advantage of quantum is that if you look into this particular, this one. If you look into this particular scenario, okay, the quantum generates the entire distribution at one shot. Due to the superposition principle, n qubits can distribute a 2 to the power n, generate 2 to the power n number of basis states. Okay, right? And you can plan and map the entire 2 to the power entire distribution on 2 to the power n. Means if you have n number of samples, in a distribution, you require log n qubits to represent a distribution. And then you can work on the entire distribution at one shot. So you are learning the distribution at one shot, not sample and sample. But the problem in the quantum is that though you can pass the entire distribution, but when you are taking out from quantum system, it will only have one state. It will collapse to one state due to the collapse of the quantumness when you do the measurement. So now quantum algorithms are those algorithms where you actually, so what we do that after initialization, we do the quantum operations. The quantum operations are done and that's the quantum algorithm. So quantum algorithm is very different like classical algorithm. It's not works in the same way. So quantum algorithm is that algorithm which will try to start from a very evenly distributed distribution to a very squeezed distribution. And suppose your problem is such that out of a large number of samples in the distribution, I need to pick, that means any 3 samples, which are far better than the others. If this is the problem you are trying to work out, then quantum will do very good, because quantum has the power of power of interference. So the quantum operations, which are single qubit and 2 qubit operations, will ultimately collapse some states, majority of the states, and will amplify only certain states, right? And that means for this example the answer is very good because you have only one state amplified, but normally it will not be like that. It will be most of the states collapsed and some states will be will have a higher amplitude, and then the measurement probability is that means the measurement probability tells you that the square of the amplitude is the probability. So some of the states have a very, very high amplitude. When you measure the quantum system, it will fall on that state. And your problem is solved because you didn't wanted to only choose the best. That means you are satisfied if we get the from any 4 best or from any 3 best samples, any one, you are fine. So those are the things where quantum works very good. So that's the scenario of quantum. But this process of actually generating the quantum large state and converging to the result very fast, inherently attacks the scenario of cryptography, where you need to find out the factors of a large number, right? And those are the keys, prime factors of a large number, and those are very hard in classical. But quantum, you can search, you can generate a lot of possibilities, and then you can converge to a few possibilities very fast from classical, and that itself actually attacks. So if I have a quantum system, right, I can attack the present crypto systems very fast. So we have to build the next channel, which is called post-quantum cryptography. Not getting into this, but this is also our latest, that means the latest architecture. As we are always going for the edge. So we are also trying to see that how post-quantum cryptography can work on edge. Post-quantum cryptography challenge is it's very heavy cryptography, a lot of computation. So this is a recent transaction on circuit and computational area design paper, TCAD. Transactions on dependable on system computing. So this year we published, right? And this is also a paper where we showed that how we can break up the maths of the PQC to a little bit better way, some approximate way. It's not the exact we are doing, but we are breaking up into some approximate way. And we have that approximation leads to a lot of lightweight computation of the PQC at the edge, right? And probably we have to prepare this PQC because this is the next level of cryptography which is coming up. So I think I am done up to this. So this is some of the things which India is going on. You can look into this. India, as I said, that India is going on very heavily on the digital public, semiconductor mission, and the compute mission. Okay, the National Supercomputing Mission is trying to give an access to everyone a supercomputer. Everyone can access supercomputer. Okay, to the India Supercomputing Mission. Okay, right. A lot of companies have come up in the Indian domain that to develop this. Okay, and sovereign AI and all these things, accelerated R&D in AI, all things are going on. Okay, these are the two national missions which are going on. Okay, I am a very core part of National Quantum Mission. Okay, one of the members of National Quantum Mission in our country. So these are the two big missions going on, right? And I conclude here that I think the compute and data stack, I think the sovereign compute and data stack is now coming up. Every country is building their own data, right? Because it's very important, right? I cannot build that means you cannot build your tea plantation model by taking the model for my tea plantation, because it is very different. Your soil condition, environmental condition is very different. So we have to build your tea model on your data. Okay, right? You cannot take one country's data and build a model for other country. You cannot do it. You have to have a sovereign data, sovereign model policy for every country is going on. Okay, AI, HPC, quantum is one of the triad. Post-quantum is the direction. And obviously Industry 5.0, physical AI and edge, cyber physical system is also the direction. So these are the directions. Maybe in the next 2-3 years, we will see that whether my predictions are going in the right, have gone in the right direction or not, okay? Yeah, so this is my current team. It is not that whoever has worked with the paper with me, these are all the names. This is the current team which I'm working with a team from IIT Kharagpur and University of Calcutta. Okay, right? I am here to get some problems from you. Okay, so that means if you want to interest, right? I have a very strong team in every domain: security, AI, that means high performance computing, right? The team is very well balanced. Okay, I just only that we give them and discuss and try to motivate them to do work. Work is done by them only. I am only motivating them to do good work, okay? Yeah, thank you all. And these are some sources, some references you can get into. Okay, so thank you.